Let's consider the winding of such a product as small attitude control thruster. Combustion chamber and nozzle, a single surface with a tight throat. Convex-concave generatrix. We are setting up the winding calculation.
What makes this one different from any other convex-concave mandrel?
Scale and purpose. This isn't a structural tank or a mast. This is a precision component that operates under extreme thermal and mechanical loads. Every layer of tape must be placed with intent. The throat is the critical section. It's where the flow chokes, where the heat flux peaks, where the stresses concentrate. And it's also where the winding process is most constrained. We load the profiles. Set initial pole opening radii, injector side and nozzle side. Winder CAM computes the geodesic trajectory. The winding angle there is around 80 degrees. The tape crosses nearly circumferentially. That's unavoidable. It's dictated by the ratio of the pole radius to the throat radius. Clear out doesn't give you much room to maneuver.
So what's the challenge?
The challenge isn't whether the tape crosses, it will. The challenge is what happens on the other side. The carriage kinematics. The thickness distribution. The layer-to-layer evolution of the surface. And ultimately whether the finished part meets spec. People think the difficulty with convex-concave mandrels is the geodesic constraint. It's not. The constraint is clear: our pole must be less than our throat. Once you satisfy that, the trajectory exists. The real work begins after that.
Which is
Designing the winding sequence. How many layers? What angle for each? Which direction? Do you alternate helical and hoop layers near the throat? Do you accept a small carriage reversal if it gives better coverage? These are the questions that determine whether the part works.
not whether it's windable, whether it's well wound.
Exactly. Windable is a low bar. Well wound, that's an engineering achievement. Now consider the multi-layer problem. After the first layer, the throat geometry has changed. The radius is larger by the thickness of the tape. The clear-out constraint relaxes slightly, your R-throat has increased. But so has the outer profile everywhere else. Each subsequent layer sees a different mandrel.
So the winding parameters should evolve layer by layer.
Ideally, yes. You might start with conservative pole openings on the first layer to ensure clean passage through the throat. Then, as the throat radius grows with each layer, you can open up the pole radii, steeper winding angles, better coverage, faster deposition. Winder CAM tracks the accumulating thickness and lets you adjust parameters per layer. You're not winding a fixed mandrel, you're winding an evolving one. This thruster is just one example. The same principles apply to any convex-concave component with a functional throat. Rocket nozzle extensions, both solid and liquid motors. Venturi flow meters for the oil and gas industry. Pinched aerodynamic ducts in UAV airframes. Necked pressure vessels for satellite propulsion. Anywhere you have a constriction that serves an aerodynamic, thermodynamic, or structural purpose, it must also survive the manufacturing process.
So the winding process becomes part of the design, not an afterthought.
That's the shift. 30 years ago, the designer drew the profile and the manufacturing engineer figured out how to wind it or not. Today, with tools like Winder CAM, the designer iterates the profile and the winding parameters together. The manufacturability feedback is instant. The throat geometry, the pole openings, the layer sequence, they are designed as a system. Winder CAM turns winding from a trial and error craft into a predictable engineering process. You vary the parameters, pole openings, layer angles, sequence. You see the trajectories, the coverage, the thickness accumulation. You find the operating window.
The window is narrow, but it's there.
And it's found by computation Winder CAM, try it.